I wanted to talk about a few Bootstrap problems that I didn't quite have time to go over in our class on Wednesday morning. So I'm going to pick up where we left off actually and load in the data sets that we had been working with. So the BAS 471 movies.r data file has a bunch of data frames that talk about user ratings and various movies. So what I'm going to do is illustrate how to use the Bootstrap to answer some basic questions about how ratings differ from one group to another and how ratings for various movies are related. So what I'd like to do is start out by defining a data frame called active, which is a subset of the typical data frame where n is at least 1000. So what is this? Well, this is simply a subset of the user's ratings of those users that are fairly active on that Movie Lens website. So some users have rated a lot of movies, some hardly any. Active now is going to be a data set of those users that have rated at least 1,000 different movies. So very active here. Looking at just the first few rows, we're going to be studying the typical rating of these users. We want to study something about that distribution. So the first thing I want to look at is the confidence interval for the average value of this typical rating here. So if I make a histogram, I'm assuming that there's some probability distribution that is making these values, and I'm interested in knowing what mu, the expected value or average value for this probability distribution is. I don't know what the name of this distribution is. I don't really care at all. I just want to know what's its value of mu. Well, here's how we bootstrap it. So we know that the average that we've measured in the data itself is probably close to mu. The sample average is an unbiased estimator, and we have a pretty good idea of how far off it might be from mu. 3.25653 is kind of our best guess. The standard error of that, once again, is just the standard deviation of the values we see there, divided by the square root of the number of observations in our sample, so n row of active. We think that our guess of 3.256 is likely about 0.008 or so away from what mu is for this probability distribution. But let's come up with a range of values that are plausible for mu based on this data. Let's come up with a 95% confidence interval. And so here's how the Bootstrap procedure works. What we're going to do is we're going to generate alternative samples. I'm going to call them boot samples here, by picking with replacement from the originally recorded values. So we'll put replace equals to true so that we can pick the same value twice potentially. This will generate a sample of equal size to our original data. And this represents how our data could have turned out. So the sample average that I measure from here is a possible sample average that could have arisen maybe in an alternative universe. And I'd like to know, well, just how variable can these sample averages be from one alternative sample to the next. So that makes a Bootstrap sample. This measures the average on that Bootstrap sample, so pretty darn close to what we measured in our original data. But if we build up enough of these Bootstrap samples, we get an idea for how much variation we see in the sample average from alternative sample to alternative sample, so we get an idea of how far off our one sample average might be from mu. So what we do is we say, okay, let's just go ahead and record the averages of all these Bootstrap samples as we generate more and more of them. So I'm going to write a for loop that takes us through 499 Bootstrap samples. In each of these iterations, I create that Bootstrap sample, and then I record the value of the sample average of that Bootstrap sample. And once I've run this, well, if I ask for the quantiles of the Bootstrap averages that I measured, specifically the 0.025 and the 0.975 quantiles, that lets me know what a 95% confidence interval is. So over these alternative realities here, I've measured a bunch of different potential sample averages. The philosophy of the Bootstrap is if you take the 2.5th and 97.5th percentiles of those Bootstrap averages, well, you can use that as the lower and upper limit of a 95% confidence interval. So it gives you an idea for how far off your one observed sample average from your data might be from you. So in this case, we're 95% confident that the average typical rating among these active users is somewhere between 3.24 and 3.27. So we've nailed it down really quite accurately, it looks like. If I run t-test on the original data values. For such a large sample like what I have here, I'm going to find that these two confidence intervals actually match up really quite closely. The nice thing about the Bootstrap is I didn't need to make any special assumptions about the data. I didn't have to do any math whatsoever. I essentially lifted myself up by my own bootstraps to come up with this confidence interval. And this works for a lot of different statistics. Here we were measuring the sample average of each one of those Bootstrap samples and using that to estimate the average of the probability generating distribution. Well, if I wanted to basically estimate some other parameter of this distribution, maybe like the 20th percentile, well, I can go and just measure the 20th percentile of all those Bootstrap samples. So very easy to generalize to different statistics here. I'm just going to call this, instead of boot.means, just boot.perc for percentile. And what I'll do is for each one of those Bootstrap samples, they're still generated the exact same way, I'm just going to go and measure the 20th percentile. I'll run the quantile function on the Bootstrap sample values and extract out that 20th percentile. So if I want a 95% confidence interval for the 20th percentile of this probability distribution, I can say I'm 95% confident that it's somewhere between 2.92 and 2.96. So come up with some parameter of that probability distribution you want to estimate, the mean, the median, standard deviation, percentile, and you can get a confidence interval via the Bootstrap by programming it this way. Now, because bootstrapping is so popular, there's a whole library to do this bootstrapping. Library boot, you might need to install .packages and then in double quotes boot to get it down onto your computer. But once you've done library boot, you've loaded it up and you're ready to actually just have rs command do this programming for you. And you get a little bonus. You can run an improved procedure for coming up with a confidence interval called the BCA procedure, which is an improvement over the percentile procedure that we just programmed. So how does this work? Well, we write an estimator function. We always start out by typing it out as this. Basically, we say estimator left arrow function, and then x and indices. And then what we need to do is write what we're going to measure about each Bootstrap sample. So if I wanted to estimate, say, mu of this probability distribution using the sample average, well, I'd want to get the average of each one of those Bootstrap samples. Now, how do I do that? Well, since I am referring to the Bootstrap sample values by the letter x, it's like I'm taking the mean of x, but estimator wants a bracket indices. Wherever I refer to an x, I want to make sure to put a bracket indices here, which matches up with the name of the second argument, so that the reference to the Bootstrap sample is done correctly. But once that estimator is defined, I can run the boot command, put in my original data here, so active $rating, estimator, the name of this function, and then say how many Bootstrap samples I want, 499. Does it just like that, and then I can ask for a Bootstrap confidence interval. First argument will be capital boot, and then type will be either PERC in quotes for the percentile Bootstrap confidence interval, so 95% confident that the average of this probability distribution is somewhere between 3.24 and 3.273. This is what we measured back when we programmed it ourselves. And I can also ask for the BCA confidence interval just by adding in BCA in quotes here. Now, if you get this error, like what I have here, it turns out that we just didn't make enough Bootstrap samples for this improved procedure to actually work. So if you get this error, you didn't do anything wrong, you just didn't have enough Bootstrap samples. If instead we make just about 5,000 and rerun this command, it'll be able to figure out the special adjustments that it needs to make in order to improve what that 95% confidence interval looks like. It takes a little bit longer because there's more Bootstrap samples, but after the end of it, we will get a nice Bootstrap BCA method confidence interval out. And so we see in this case, actually, there's extremely little difference between the BCA method and the percentile method. But when you can afford the time to actually get the BCA method, that's what you want to do. Its level of coverage is going to be closer to that target 95%. So what if we wanted to get a Bootstrap confidence interval for the 20th percentile? We had programmed it right here. How would we change this estimator function? Well, instead of measuring the average of each of these Bootstrap samples, we'd be measuring the percentile of that sample instead. So quantile, X bracket indices, whenever we're referring to the Bootstrap data values, that'll be X bracket indices, and we just put in a 0.2 right here. So we update our estimator, we set it running, and then we wait. And so it's completed, and in this case, once again, no difference in this case between the percentile Bootstrap interval and the BCA confidence interval here. Typically, that BCA correction really only plays a big factor when you're dealing with a relatively small sample. And in this case, we're not dealing with a small sample at all. We have 2,700 individuals in here. So the BCA correction wasn't all that necessary, but it's always good to know about. Always run it if you can. Now, one more example of the Bootstrap, something a little bit more complicated. What if we wanted to come up with a confidence interval for the difference in the 20th percentiles of two different types of raters on the Movie Lens dataset? So we have these active users. Those are the ones that have at least 1,000 different movies being rated. Let's also make a subset for casual users, ones whose number of total movies rated is between 20 and 22. So it turns out there's actually quite a lot of users in the data set like this. There's over 12,000 different casual users. We might like to know, well, how do the percentiles of these typical ratings differ between these two types of users? So if I were to come up with a best guess, well, I could go and just measure the 20th percentiles of both of these types of users. So typically, if you're extremely active, the 20th percentile, the typical rating, is right at around 2.9. If you're more casual, well, your 20th percentile, let's see how that differs. It's actually a little bit higher. So maybe if you're more casual, you kind of focus in on the movies you like. Maybe you typically assign higher ratings. We see a difference of 3.15 minus 2.94, basically 0.212. So we know that's probably close to the difference in the 20th percentiles of whatever two probability generating distributions are making the data that we've collected here. But we want to take it a step further. We want to come up with a range of plausible values for this difference that's consistent with the data that we've collected. So just looking at the two distributions, that's the distribution of the typical ratings we get from all of those 2,700 active users. Here's the distribution of the typical ratings the casual users are providing to us, a little bit skewed up towards higher values. How big of a difference in 20th percentiles, kind of at the lower part of this distribution, are we talking about? So boot package really won't help us out in this case since we have two different samples here, but we can program it pretty easily. I'm going to make a vector called boot.diffs, which is going to store the differences in these 20th percentiles when we make Bootstrap samples here. So I'm going to make 4,999 different Bootstrap samples, and I'm going to make two Bootstrap samples, one for the actives and one for the casuals. So I'm going to make a Bootstrap for the actives just by sampling with replacement from those ratings among active users. Replace equals true. And I'm going to do the same thing for the casual users. So I'll make a Bootstrap sample for the casual users as well. And then what I can do is measure the 20th percentiles of each one of them and get the difference. So let's get the 20th percentile for the active users, subtract off the 20th percentile for the casual users, making sure that we're just using the Bootstrap samples that we've created. And so we've programmed it. So we've made a Bootstrap sample for the active, Bootstrap sample for the casual users, measured the 20th percentiles for each, and we're storing those in boot.diffs. Once we've gone through and made those 4,999 Bootstrap samples, we get an idea for how much the difference in 20th percentiles bounces around from Bootstrap sample to Bootstrap sample, and that is really quite informative as to how far off our originally measured difference, which we just calculated to be 0.212, is likely to be from the true difference in 20th percentiles. So how do we get our Bootstrap confidence interval out? Well, we simply ask what is the 0.025 to 0.975 percentiles of what we measured over the Bootstrap samples. And so in this case, we find that we're 95% confident that the difference in 20th percentiles between active and casual typical ratings is somewhere between 0.245 and 0.189. They're all negative, indicating that the 20th percentile for active users is smaller than the 20th percentile for casual users, but notice that 0 is nowhere inside this confidence interval, so we have found a statistically significant difference in 20th percentiles of these two distributions. And I think this really illustrates the power of the Bootstrap. I literally have no idea how to actually get a 95% confidence interval out for the difference in 20th percentiles of probability generating distributions. I don't even know if anyone sat down and actually worked that out mathematically. The Bootstrap, as we can see, boom, we can just program it and come up with a pretty reliable procedure for coming up with a range of plausible values based on the data that we've created. And in fact, I want to show one more kind of advanced illustration of using the Bootstrap to estimate something that would be very difficult to do unless you were very well versed with a theory. So one of the other data sets that's stored into that saved environment file is movies, and these were user ratings for two movies, The Shawshank Redemption and The Usual Suspects. So what I'm going to do is I'm going to restrict my analysis to users that have rated both of those movies. That's what these first three lines of code are doing. It's creating a data frame where the users in the both data frame are ones that have given a rating for Shawshank and for The Usual Suspects. And then I'm going to make two different data frames, just the ratings for Shawshank Redemption and just the ratings for The Usual Suspects. We can see that the user IDs in both the different data sets match up, so the 10th row in both of these data frames give us the rating for both these movies of the 10th user in the data set. So the Shawshank Redemption ratings are matching up with The Usual Suspect ratings. And so I can do some sort of analysis here. Maybe there is some way to predict one score from the other. Maybe I'd like to get a 95% confidence interval for the predicted rating of The Shawshank Redemption when I know that someone's rating for The Usual Suspects is 3.5. That sounds like a job for a linear regression, and you could go back to your BAS 320 notes and look up how you would actually get confidence intervals for this sort of quantity, a 95% prediction interval. But we can do almost the same thing here just with the Bootstrap without actually really having to know that. How do we go about doing that? Well, let's go ahead and define y and x. Y is always that thing we're trying to predict, and that's going to be the Shawshank rating. What are we going to use to make that prediction? Well, that is going to be the rating of The Usual Suspects. So we know the user's Usual Suspect ratings. We want to predict their Shawshank Redemption ratings. If I define y and x, I can plot y twiddle x to get a plot of what this relationship looks like. Not a very interesting plot because we see that every combination of ratings from 0.5 stars to 5 stars are found somewhere, at least in the data set. Here's kind of a really cool command, smooth scatter. Smooth scatter x and y, as you can see, kind of represents where the points are located with some sort of color density. Now, by default, this doesn't look all that great, but if I change, say, bandwidth to a different value, like 0.5, you get an idea for where most of the data is concentrated. Most people really like both these movies, so most of the ratings are kind of 4 stars and above. But you can see that, maybe kind of, sort of, there is some sort of relationship between these two movies. Let's fit a linear regression where we predict y from x, and we can always A/B line this. Here's the least squares regression fit. So as someone's rating for The Usual Suspects gets larger, the corresponding rating for The Shawshank Redemption also tends to get larger as well. What would be the predicted value of y when x is equal to 3.5? Well, if we look at the coefficients of that model, that's the intercept of the line, that's the slope of the line, we could say, okay, well, let's take that intercept here, the first value of the coef m, and then add that to 3.5, the value of the rating for The Shawshank Redemption, times the slope, coef m bracket 2. So from our data, we would estimate that if someone rated the Shawshank Redemption as a 3.5, we predict them, oops, reverse that, X is our usual suspects rating. If someone rated the usual suspects a 3.5, we would predict, based on this data, that they would rate the Shawshank Redemption at right about 4.2 here. So that's a good guess, but what's a range of plausible values for that rating based on the data we've collected? Can we come up with a 95% confidence interval for this prediction? Well, here's how we can bootstrap it. Let's define a vector called boot.pred, of our predicted value. Initialize that as an empty vector, and let's write our for loop where we go through 499 bootstrap samples. Now, in this case, when I bootstrap, I do have two different samples here, a rating of Shawshank and a rating of usual suspects here, but I need to make sure to preserve the fact that they're matched up together. The first value in X corresponds to the first user's rating in Y as well. These two ratings go together. So what I'm actually going to do is I'm going to define a data frame where the first column is X, the second column is Y. So this way, the very first person in the data set, they rated the usual suspects a 4.5, Shawshank 5. Fifth person in the data set, 5 for both. Fourth person in the data set liked usual suspects a little bit more. And when I'm going to bootstrap, well, what I'm going to do is actually pick rows of this data set at random. That way I can keep the matching between the X and the Y values consistent. Each row in this bootstrap data frame will still contain pairs of observations that I saw in my original data. And so here's how I'm going to go about doing that. I'm going to call this boot.data. And those are just going to be rows that are picked at random from my original data frame. Since data is a data frame, when I turn on square brackets, I want to put on a comma here. Leave what's after the comma blank, so I get all the columns here. And I'm just going to say, well, let's just randomly sample 1 through n row of data. How many? Well, n row of data with replacement. So data right now has 47,000 observations. So this is the integer sequence, 1 through 47,324. This represents the row numbers of my originally recorded data. The number of observations that I need to basically pick with replacement from that integer sequence is n row of data. I need to construct an equally sized data set for each of these bootstrap samples. And I'm going to do this with replacement. There's a chance that I will select the same row twice. Some rows will be included more than once. Some rows will be excluded. But once I've created that bootstrap data sample, I can go and fit that regression line. So in this case, both Y and X now live in the boot.data data frame. And then my predicted value is just going to be the coefficient of that model, bracket 1, the intercept, plus 3.5 times the slope. Remember, I'm making a prediction when someone has rated the usual suspects 3.5. That's my X variable right here. So X times the slope plus the intercept gives me my prediction. So run it through the bootstrap here, go through 499 bootstrap samples where I've maintained the combinations of ratings between these two movies consistent from bootstrap sample to bootstrap sample, measuring the predicted value for each one of these. And so I'll be able to come up with a 95% confidence interval for what I expect to be the rating of the Shawshank Redemption when someone has rated the usual suspects a 3.5. So my best guess was that 4.19. What's my 95% confidence interval? Getting the percentiles written out right. First argument is always, what we're measuring from the bootstraps each time around. I would say that I'm 95% confident that the average rating assigned to the Shawshank Redemption when we're talking about users that have rated 3.5 for the usual suspects, I'm 95% confident that the average rating for the Shawshank Redemption is going to be somewhere between 4.18 and 4.2. So how do I actually do that back in BAS 320 land? Well, we know the theory, we know the math to actually do this. So why don't I actually do this? This is a good test for me. I haven't thought about this in about 3 or 4 years. I think I just do confident Now, predict m new data equals data frame. It's going to be a value at x equals 3.5. That's our predicted value. And, oh, I should have prepared. How do I get the confidence interval? Question mark, predict.lm, interval. Okay, that's what I had to do. Interval equals confidence. Boom. So my best guess, 95% confidence interval. Notice this is a really big sample, so the theory is going to match up very closely to the Bootstrap. Notice I basically just get that without having to remember, what I learned back in BAS 320. The Bootstrap really just is that powerful and that flexible.